Okay, so in the last lesson we talked about the Bohr model of the atom, that solar system model, and together with Rutherford's finding about the nucleus, you'll remember very keenly, I hope, from grade 9, those Bohr-Rutherford diagrams. So we're just going to do a quick reminder of some of the basic ideas and also add a little bit of detail by introducing a formula to you. So just as a reminder, in a Bohr-Rutherford diagram, you'll remember that we're going to have our positive protons in the nucleus, and we'll have our neutrons as well in there creating that mass. And then, we're going to have our electrons filling those orbits from the inside out with electrons, right? Hopefully you'll remember that. Now, of course, in the last video, we sort of dispelled a little bit of this by introducing Schrödinger and Heisenberg's ideas. That's not to say that we can't glean some really important information from the Bohr model that helps us to make predictions about atomic behavior and molecular behavior. So without further ado, let me introduce this formula to you. So this formula here that you're seeing, x is equal to 2n squared, it allows us to predict the number of electrons. So the number of electrons in a given energy level n. So this n represents the energy level according to Bohr's model, right? And so if we know the energy level that we're talking about, we can predict how many electrons maximum can fill that specific energy level, right? So let's analyze this a little bit. And it's going to kind of just add a little bit of detail to your current understanding of what atoms can look like according to the Bohr model. So if we look, for instance, if we're trying to figure out the number of electrons in the first energy level, then n would be equal to 1, right? So 2 times 1 squared, of course, 1 squared is 1, and then times 2 is 2. And we know that. We know that in the first energy level, we can have a maximum of 2 electrons. Now let's look at our second energy level. So this is for n is equal to 2. Where n is equal to 2, then we can say that x is equal to 2 times 2 squared. Well, 2 squared is 4. And then times 2 is 8. And so this is following the pattern that we would expect, right? But let's take a look at our third energy level, where n is now equal to 3. Right? We have x is equal to 2 times 3 squared. Well, 3 squared, we know, is 9 times 2 will give us 18. So that's a bit of a bit of a difference in that, most of us will remember filling electrons from the inside out, where there being 2 in the first energy level, then 8, and so on and so forth. So what we're describing here is the maximum number of electrons allowable at that energy level. We're not talking about what makes an atom stable. And so if we continue this pattern, we'll see that, when n is equal to 4, we end up with 2n squared, 2 times 4 squared, which will give us 32 overall. So this, of course, is describing the maximum number of electrons, not the number of electrons that will allow an atom to be stable. And so some of these patterns we'll revisit when we get to grade 12 chemistry in that first unit about quantum mechanics and electron configurations. So hold on to that for now, but we're going to press pause on that and just remind you about the basics of Bohr-Rutherford diagrams. All right, so moving on. So what you need to know for this year is that when we look at the first element, the first 20 elements, okay, so we're going to stop at calcium here, because calcium kind of marks the spot where beyond that we end up looking at the transition metals. And you've heard me mention in class that once you get to the transition metals, things get a little bit wonky. And so we're going to leave that discussion to grade 12. So what you need to know is up into calcium, i.e. elements with 20 electrons, we're going to say that that third orbit or energy level is going to be stable with 8 electrons. And we're not going to fiddle too much with doing the Bohr-Rutherfords beyond element 20, because that's where things do kind of not, they're not exactly ideal, and we can't really use the trend on the periodic table to help us predict atomic configuration, electron configuration. So what I want to do is just quickly use chlorine as an example to remind you about Bohr-Rutherford diagrams. So chlorine, when we look at it, we can see that it has 17 protons. That's its atomic number. And if we're talking about neutral chlorine, then it will also have 17 electrons. So it's going to have electrons and protons are going to be 17. And then we know if we look at another periodic table, you'll see that its atomic mass is 35.45, which makes its mass number 35. And we do the subtraction here, and we can see that the neutrons are going to be 18. All right, so in drawing our Bohr-Rutherford diagram, we're going to create that nucleus, and we're going to show it having 17 protons, oopsies, and then 18 neutrons. And then we need to house these 17 electrons in orbits, right? So according to Bohr. So I'm going to put 2 electrons in that first energy level. And so we've used now 2 out of the 17. We have 15 left. Create another orbit. Right, and now I'm going to start filling, and I'm going to go around the world first here. So 1, 2, 3, 4, before I start pairing up. 5, 6, 7, 8, and that idea will also become more meaningful in grade 12. So now I've used up 10 of my electrons. I've used up 8 more, and so that leaves me with 7 left. And so I'm going to fill that outer level with 7 electrons. But again, I'm going to go around the world first here before I pair up. And now I'm done. There's just our quick reminder of how to do a Bohr-Rutherford diagram in case you needed a refresher. So again, this year we're going to look at, there being 2 electrons in the first energy level, 8 in the second, and then our third energy level will be stable with a max of 8 electrons. All right, so there's going to be another worksheet that you're going to find just reminding you of some basic ideas relating to trends in the periodic table, which I'm going to urge you to spend some time really understanding, because those basic ideas around charges, valence electrons, ionizing, and all that is super, super critical, foundational. They're foundational pieces for the rest of the course. So do spend the time investing in making sense of them. And reach out if you have any questions.